Welcome to the deep dive. Today we're tackling something pretty auspicious.
We really are.
A look inside the proof of the geometric Langlands conjecture. Now this is, well, it's a huge area connecting representation theory and algebraic geometry.
Two massive continents of mathematics, you could say.
Exactly. Think of it like finding a kind of Rosetta Stone linking these different mathematical languages.
hmm
Our goal isn't, to master it all today, but more to get a real feel for how this proof is being built, especially across a series of recent papers.
Right. And geometric Langlands, it's excited because it points to these really fundamental unities in math. The cool thing is we actually have this series of papers mapping out a path,
A potential path to the proof.
a potential path, yes. And we want to focus on understanding how the argument develops, sort of from the first paper team to the fifth, even if we mostly dig into the early stages today.
This is really cutting edge research happening right now.
Yep,
And the main text for our discussion today is the second paper in that series. You can find it on Arxiv, number 2405.03648.
that's the one.
And this one seems pivotal. It really dives into the interplay between something called Kac-Moody localization
Which is a big tool in representation theory.
and this global geometric Langlands functor, which sounds like a main event
It's
almost.
certainly a key player, yeah. It bridges the local picture and the global picture. We'll also see how it builds on paper I and sort of sets up what's coming next.
And you mentioned before we started the Balance and Drinfeld approach is important here.
Hugely important, yeah. Instead of just looking point by point, they encourage looking at families, over curves, or even higher dimensions. It gives you a much broader view.
Reveals deeper patterns, maybe.
Exactly. And it heavily uses chiral homology or factorization homology. It's a way to build global things from local bits that interact.
Okay, like understanding a machine by how the little pieces fit together.
Yeah, precisely. Especially how they behave when they're, physically separated on the curve.
All right, that gives us a framework. So let's dive into paper 2, 2405.03648. What's like the core result or idea they're tackling?
Okay, so a really central result is Theorem 18.5.2. Lays out this crucial relationship involving a space called ILI.
G-check,
G-check, yeah. It helps organize, roughly speaking, local systems in these things called opera structures.
which are like specific differential equations.
Kind of, yeah. And the theorem connects this spatially to two important functors, loc crit and locop g crit. The key takeaway is that loc crit basically goes through locop g crit.
Goes through, okay, so locop G, crit is like a necessary stop on the way. What are these functors actually translating between?
Think of them as bridges. Loc crit connects things related to our group G to this world called D mod crit bunk.
Okay, D modules on the stack of G bundles. That sounds geometric.
Very geometric. Bunk catalogs all the ways you can bundle G over your curve. Locop G crit maps from a related world tied to opers to that same D mod crit bunk.
Oh, okay.
So saying loc crit factors through locop G crit suggests that maybe these opera structures are a more fundamental route to understanding those D modules.
The paper also mentions rep, ran linearity, and the Hecke action. What roles do they play?
Right, so rep ran deals with how representations of the Langlands dual group behave over this Ram space.
Which considers collections of points on the curve.
Exactly. Linearity here just means the functor locop G crit respects this representation structure. And the Hecke action, well, that's fundamental for D modules on bunk.
That's about modifying the bundle at points, right?
Precisely. You modify the G bundle at a point, and the Hecke action tells you how the D modules respond. The fact that locap G crit respects this action connects the representation theory of directly to the geometry of bunk. It's a deep link.
And what about Kac-Moody representation theory at the critical level? Is that just jargon, or is the level itself significant?
Oh, it's very significant. The critical level is a special parameter in Kac-Moody theory where things often simplify dramatically. You get connections to conformal field theory, quantum groups, and crucially here, geometric Langlands.
A mathematical sweet spot.
You could call it that, yeah. Structures align in interesting ways at the critical level.
Okay, then things get a bit abstract. A multiplicative factorization, 1-2 gerb on elegy. What's the intuition?
Okay, yeah, that's a mouthful. Think of a gerb as like a bundle with extra layers of complexity. 2 points to a specific kind of twisting.
Like a square root kind of twist.
Sort of related to square roots of unit. Multiplicative factorization means this twisting behaves well when you combine loops elements of the loop group, Ln.
Which are maps from a punctured disk into G.
Right. And importantly, this twisting simplifies, it becomes trivial on certain well-behaved subgroups of LNG, like L plus G loops that fill the whole disk and LN.
Why Ln?
Ln is topologically simpler in a way. It gives you a place to naturally untwist the structure, which is technically very useful.
Right, okay, we're building layers here. Now, geometric Satake equivalence, ATG, and Feigen-Lustig equivalence, FLE, these sound like big deals.
They are. Absolute cornerstones.
Corollary 1.8.5 connects them. What's the core idea there?
So geometric Satake, SASTG, is this amazing dictionary. It connects representations of the dual group to the geometry of the affine Grassmannian for G.
An infinite dimensional space related to G.
Mm-hmm. And the Faergelistic equivalence, FAOD, connects certain quantum group representations to affine Kac-Moody representations at the critical level. Okay. Corollary 1.8.5 essentially says these two massive equivalences are compatible. The relationship between rep and a category called wit. The Whittaker category, established by FLE, fits perfectly with the Satake picture via objects called SPHG and speculae.
So it's showing consistency between these major theories.
Exactly. It strongly suggests the G and A duality runs really deep.
Then we hit Mon-free opers in categories like incote, exum, Mon-free. What are Mon-free opers?
Mon-free basically means the opera behaves simply near singularities, no monodromy. These incote categories are ways to organize functions, or sheaves, on spaces of meromorphic opers that can have poles.
And Mon-free focuses on the simple ones.
Right. The equivalence mentioned, using the incote half functor, lets us understand these simpler Mon-free objects within the bigger picture of all meromorphic opers, like studying a clean wave within a messy sea.
Makes sense. And the thought functors, thoughtmer and thoughtbreak, elated to self-duality.
These SAR functors point to symmetries within these categories of sheaves on opera spaces. Self-duality means an object is essentially its own dual.
Which often signals deep structure.
Often, yes. It's a sign things are tightly constrained and elegant.
Then there's PZ, connecting inco as Z to Q-co-co-Z, another translator.
Exactly. It translates between incoherent sheaves on these potentially complex and schemes V and quasi-coherent sheaves, which are often more directly tied to algebraic structures. It helps bridge geometry and algebra.
Okay. The factorization functor in cohen and proposition 4.4.7 sounds technical. The gist.
The enhanced functor, Rin-Coab an, formalizes that factorization idea, how things behave on disjoint regions. Prop 4.4.7 is a key technical result saying this functor works really well, it's an equivalence, for certain well-behaved subcategories.
Why is that important?
It lets us confidently connect the geometry, sheaves on opera spaces, to algebraic objects that naturally have this factorization structure.
And the Drinfeld-Sokolov reduction functor, DSN hat, how does that fit with Avoy?
Drinfeld-Sokolov is a powerful way to simplify things. It relates Lie algebra representations to smaller, related algebras called W algebras. This enhanced version connects critical level representations of the affine Lie algebra I to our Mon-free opers.
Ah, linking back to the opers.
Exactly. And the fact that this reduction is tied to the critical level Feigenlustig equivalence, Fleig-Crit, just reinforces the deep interplay between representation theory and the geometry of opers.
We also see Zaghi-G, the Feigen-Frankel center, acting on the vacuum module of Crit. Theorem 5.2.5 connects this to ret module categories.
Right. Zaghi-G is a crucial bit of algebra acting on a fundamental representation, the vacuum module. Theorem 5.2.5 says the functor associated with this action lifts nicely into the world of representations of the dual group Eike.
Another sign of geosymmetries.
Very strong sign, yeah. It shows the structures on both sides are intimately related.
Then proposition 6.2.4 and theorem 6.2.2 use Fleig-Crit to relate KLG-Crit and Incubiad-Uppenfree-Crit. This sounds central.
It absolutely is. These results show that Fleig-Crit really is the bridge. It provides an equivalence between G's representation theory, KLG-Crit, and the geometry on the ad side, Inco and Uppenfree-Crit.
And it works with factorization.
Crucially, yes. It's not just point by point. It respects the local to global structure via factorization functors. Prop 6.2.6 underpins this, showing good local behavior implies good global behavior for these functors.
And the commutative diagram in section 6.3.6, just a consistency check.
Pretty much, yeah. It shows that routes connecting these various categories using Grinfeld-Sokolov, including Mon-free, into meromorphic opers, all line up. It builds confidence that the whole framework hangs together.
Okay. Then there's a quick mention of matching Plock G and Plock under the equivalences Fleig-Crit and Fleig. Local global compatibility again.
That's the idea. These Plock functors manage the local global traffic. Showing they match up under the main equivalences means the correspondence works consistently at both local and global levels, on both the G and I sides.
The paper then introduces crystals of categories over Rham and local-to-global functors, formalizing the local-to-global idea.
Precisely. A crystal of categories gives a rigorous way to organize the mathematical data associated with different finite sets of points on the curve, making sure they mesh correctly. Local-to-global functors are then the tools to build global results from this structured local data, essential for handling factorization properly.
and unital factorization algebras and strict unital functors. Lock being strictly unital sounds positive.
Unitality here relates to how things behave with respect to the empty set of points, a kind of identity element. Strict unitality means the functor respects this identity perfectly.
A sign of good behavior.
Yes, it suggests the functor lock is well-behaved and predictable regarding these fundamental structures.
We also see quick mentions of affine D-schemes and factorization spaces like LROC-Y, background machinery.
Yeah, those are more advanced tools. Affine D-schemes incorporate differential operators into geometry, and spaces built from them naturally have the factorization structure we need. They're part of the technical engine running underneath.
Lastly, the dual category DMOD 1-2 Alpong, Wit byte Ran, and the functors A and Lock G. More connections being established.
Correct, more pieces of the puzzle. DMOD 1-2 avoid Kobung involves D modules with certain properties, coef G and point G linked to the Whittaker category again. And edg of 2 alcohol are an adjoint pair connecting global D modules on bunk back to the representation category, KLG Ran, another facet of the duality.
Okay, so we spent a lot of time unpacking paper 2, but it's crucial to remember this is just one step in a 5-paper sequence.
Exactly.
Paper 2 itself points back to paper I, GLC1, for the definition of the geometric Langlands functor.
Right, setting the stage.
And it uses a result from FG2 about the Faergeman equivalence, so you can see how it builds.
Absolutely, the proof strategy is clearly sequential. Paper I lays foundations, defining the main object. Paper 2 uses that definition, plus existing results like the one from FG2, to establish these crucial critical level equivalences we've discussed.
And presumably papers the third, IV, and V will push further.
And that's the expectation. They'll likely need to tackle other aspects, perhaps bringing in derived Satake more heavily, delving deeper into Feigen-Frenkel duality, maybe making connections to W algebras more explicit to build towards the full conjecture. Each paper leverages the previous one.
Now, wrapping up our look at these initial stages, especially through paper 2, what's the big picture strategy we're seeing emerge for this proof?
We're seeing a strategy based on establishing really deep equivalences between different mathematical worlds, representation theory on one side, geometry on the other.
Bridged by functors.
Bridged by functors, exactly. Key tools are factorization homology for the local to global aspect, and major known equivalences like Satake and Feigenlustig acting as pillars.
And specific techniques like using the critical level Drinfeld-Sokolov.
Right, exploiting special structures like the critical level in the Feigen-Frenkel Center. The step-by-step progression from I to 2, building on definitions and prior results, seems characteristic. It sets up the exploration of further symmetries and dualities needed later on.
It's really quite something. Even this glimpse shows how intricate and interconnected it all is. We've definitely skipped over a lot of the deep technicalities.
Necessarily, yeah.
But hopefully you, the listener, get a sense of the kind of profound relationships being mapped out here and how this proof is unfolding piece by piece.
Absolutely. And if you are intrigued, the papers are out there on Arxiv. What we've talked about gives you maybe a starting point, a framework for trying to grapple with this research as it progresses through the whole series.
And maybe a final thought to leave you with. How might these incredibly abstract connections, these dualities between algebra and geometry, how might they point to even deeper, more fundamental structures in math itself? What completely new ideas might spin out of understanding this?
It's a fascinating question. What happens when you fully map one world onto another?
What indeed. Thanks for diving deep with us today. Oh, hey there, what's up?
Well, thank you so much. We really appreciate that you're enjoying it.
It's fantastic to hear you're finding it amazing.
You're asking if we can go into great detail about paper V and also the first 4 papers.
That's a really ambitious dive.
It is, given the depth of even just this one paper we've been discussing.
To go into that level of detail for all 5 right now?
It would likely take us quite a long time, probably well beyond the scope of this session.
But we can definitely talk more about how paper V builds upon the others.
Absolutely. Paper V, which is Arxiv number 2409.07051, focuses on the multiplicity 1 theorem.
And to get there, it really relies on the groundwork laid in the first 4.
Exactly. In its introduction, section point 1, it even begins with a short summary of the key points from GLC1, GLC2, GLC3, and GLC4.
So it assumes you have some familiarity with those earlier results?
Yes. For instance, it reminds us that GLC1 defined the category of half-twisted D modules on bunk.
which is central to the whole de Rham version of geometric Langlands.
Right. And then paper V, even though it focuses on a global, untwisted, unramified de Rham setting, as they mentioned in section 0.4.2.
Still draws on those earlier foundations.
It does. It uses dimension counts, similar to some of the tricks discussed in section 0.2, to analyze automorphic sheaves.
And section 1 of paper V is specifically a summary of the results from the first 4 papers that will be used in its proofs.
So in a way, paper V acts as a culmination, bringing together many of the threads developed earlier.
It also states in section 2 that it's sufficient to prove GLC for almost simple and simply connected groups.
A simplification that likely relies on reduction established in earlier papers.
And section 5 of paper V gets into proving GLC for curves of genus greater than or equal to 2.
Elaboration on outlines is given much earlier in the series, as mentioned in its section 0.5.1.
So while we can't do a full detailed run-through of all 5 now,
We hope this gives you a better sense of how they connect.
paper V stands on the shoulders of the first 4.
It uses their definitions, their theorems, and their techniques to reach its own conclusions about multiplicity 1.
It's an estimate to the sequential and cumulative nature of this research.
Indeed, it's all interconnected, each paper building on the last.
Thanks again for your enthusiasm and your great question.
Really appreciate you joining us for this exploration.